So, good morning, ladies and gentlemen, dear colleagues. Welcome here in Milan at the EAC 2015. On behalf of the Italian Aerosol Society, I'm the president of the society. On behalf of the society itself and the organizing committee, I welcome you here officially at this edition of the European Aerosol Conference. So just a few words on the Italian Aerosol Society, which was founded in 2008. We have here the first president of the Italian Aerosol Society, Professor Franco Prodi. The society maintains a forum of researchers from various institutions and universities in order to promote collaboration in all areas of aerosol science through a number of initiatives which comprehend workshops, seminars, national conference, and now also international conference after this EAC edition. The Italian Aerosol Society became a member of the European Aerosol Assembly in 2009 and in 2012 was appointed to host this edition of the European Aerosol Conference, and we are grateful to the European Aerosol Assembly for having appointed us for this. So the scientific problem, in a few words, you will have 5 plenary lectures, 1 keynote speech, 348 oral presentations, and about 870 poster presentations. This program is the result of the excellent and huge work done by the International Advisor Committee, and I would like to thank them all for this work. Thank you so much. So you are hosted here in this fine and comfortable University of Milano-Bicocca, and it's a pleasure to introduce you the rector of this university, Professor Cristina Messa, and afterwards we have also the greetings and wishes by Professor Marco Orlandi, which is the director of the Environmental Sciences Department here in Bicocca. Please.
Good morning everybody, and welcome to our university. It's really an honor for us to have this meeting here. This is basically, I've been told the first time that the meeting is held in Italy, and the first time in Italy is in Milano-Bicocca, so it's really very good for us to have you all here, and I hope that the organization will be able to fit with the number and all the needs that you have. Our university is a pretty young university. It's 16 years old, actually. It started from the older University of Milano, which was too big, so it was split in part. And it started with a project of having a strong engagement in research for our teaching. And in fact, it started with sciences, basically, but then it moved up to medicine and humanities and many other faculties. But it started with material science and physics and environmental department, trying to elaborate interdisciplinary courses, as well as, of course, as interdisciplinary research. So nowadays, it has 32,000 students that are all around, and you have seen outside a lot of students, because just today there is an admission to a course, so it will be pretty crowded, at least in the morning. Actually, all the week is a week when you are here, but on the other side, on the other building, there are a lot of admission tests. So it's going to be a tough week for our people. So I wish to thank also all our administrative and technicians and technologists that were able to manage all these. Also, you will see the surrounding. It's quite a campus at the end, because it was built in an industrial part of Milano, where there were big industry, big farms here. Pirelli is still here, but they had all the the production of the tires, as well as Breda, as well as many other industries. So in terms of pollution and studies of environment is also very interesting, but also in terms of architecture. And you will see many places, many bars, many little areas that are really full of students, because it's quite small and it has many people around during the day. Then at night it's a little bit less crowded, let's say. Also this university has a lot of buildings, not only here, but also in Monza, where there is the medical faculty, a little bit far away where there is informatics, and many residence for students. So I hope really you enjoying staying here. I hope some of you is also going around in the area and maybe going to Expo. I don't know whether you organize something also there, because it's a good occasion at the end. And I really wish you the best meeting, and please, when there is any need and any problem, let us know it, and we'll do our best. Thank you for coming.
Good morning also from my point of view. My name is Marco Orlandi. I am the Director of Earth and Environmental Sciences Department. This department was created in 2012 from the union of former Department of Environmental Sciences and Department of Geologists. Department of Environmental Sciences was the first department created in the University of Milano-Bicocca. And from some point of view, it was the nucleus of condensation of the University of Milano-Bicocca. Since from the beginning, the study about atmospheres was one of the main research activity of the department. In the department, the atmosphere is studied from different point of view. There are physicians, chemistry, biologists, geologists, and also in this case, from the beginning, the studying of particulate and aerosol was one of the main focus. So for this way, we are really happy that there is this important conference in universities of Milano-Bicocca, and I thank very much Professor Bolzacchini to have organized this unbelievable important meeting. So, I hope that the time is quite fast, and I don't want really to waste time. And I know that you have a really interesting program and a lot of speakers. I only want to tell that again that for us this is really important. And I really give you my best wishes, and I hope that you have a really nice conference. Our director has told that nowadays in Milano, except the science, there are a lot of important happenings. There is Expo, although in this area nowadays it is quite full of nice restaurants. So I hope that not only the science will be important, but also something that can be as important as the science. Again, from my point of view, our best wishes.
So thank you very much for your greetings and wishes. And we can now move to the bursary award ceremony. We have some bursary that will be presented to the awarded students by Professor Franco Prodi, who was the first president of the Italian Aerosol Society, and by Professor Laura Perini, who is the director of the Department of Physics of the University of Milan. Please.
Let me express my emotion to be here this morning, remembering decades ago when in Italy we were 3 or 4 people in the late 60s dealing with aerosol science. And we were under the umbrella of Gesellschaft für Aerosolforschung at the time. And I remember that we had even a conference in Bologna in the early 70s of the Gesellschaft für Aerosolforschung, you see what has been achieved in the meanwhile. In Italy, we founded the Italian Aerosol Society, the European as well organized it. We have contacted with the US scientists, and we have a world organization for aerosol science. So it is a fantastic achievement. So what we are giving bursary to young people. What to say to young people? Don't forget that we are not dealing with particles. We are dealing with particles suspended in the carrier gas, and that was the thinking of Nikolai Fuchs when in his library in St. Petersburg was founding this discipline, which has become from physics of aerosol to chemistry to, so it's aerosol science. And we have to take the opportunity of this conference to the exchange of ideas, to think about what is going on in our discipline, the effect that we have bigger and bigger programs, bigger and bigger groups, but the fact remains that we have to, as in university, we learn from professors, in the conference we learn from each other. And so I wish that in this conference we have the same spirit that was through the many conferences that we had in the past, thinking to the big men which have founded and helped in this science, from Junge to Stober to Otmar Preining, to a long, very long list of people which is in spirit or in presence with us in this opening. And so I wish the best to you to enjoy this conference as we had in the past. Thank you. So we proceed to the anniversary award. We have, I will name 6 of them. Manish Agrawal from India, Ahmed Boukerit from Algeria, Pamela Dominuti from Brazil, Hama Sarkwart from United Kingdom, Joanna Leij from Portugal, Cecilia Leoni from Czech Republic.
And now the director of the Department of Physics, please.
So, I am Laura Perini, the director of the Physics Department of the older university, the one from which Roberta comes, and will add nothing to what Franco Prodi so well said. Just say that I am glad to be here and that my department could give by small contribution to this very important event. So now the bursary, Pallavi Pant, USA, Mate Pinter, Hungary.
Not arrived yet. He is at the airport now.
Okay. Angel Ludivino Varavela, Brazil.
Maybe that is also on the way.
Okay.
So anyway, many wishes to all the awarded students. Again. Thank you so much. I wish you a fruitful scientific week and enjoyed the conference, and my co-chair, Professor Ezio Bolzacchini, now will open officially this event.
Or at this point, we can open the conference. Normally, we use bells. Conference is open.
So thank you very much to our host here, and now move to the plenary. Grazie mille. Arrivederci. Everything is working. 5 minutes.
Good morning, everybody. My name is Urs Baldensberger, and I have the pleasure to chair this very first session together with my esteemed colleague, Astrid Kinter-Schar. It is quite unusual for me to start early in Italy, even before the time. But let's actually see that this is, or should we have started at 8:45? Okay, so we are right on time in Italy. Perfect. It's my pleasure to introduce the first plenary speaker, Caroline Leck. She got her PhD in 1989, and she has been now since 1991. No, she was then a postdoc, and since 91 she has been in Stockholm, and she's a professor there in chemical metrology. And if we need to characterize her in 4 words, I just can say she loves the Arctic. And she is in charge of the programs of expeditions to the Arctic and so on. She has been herself at the North Pole 4 times. Of course, the presentation will be about this area as well. The title will be Possible Links Between Marine Microorganisms, Cloud Albedo and Sea Ice Melt in the Arctic? ? The floor is yours, Caroline.
Just a second. Good morning, ladies and gentlemen and the organizing committee. I'm just waiting for the light to tune down a little bit so we will see my bright pictures. So, fine. Good. Is it 9 o'clock or should I? It is. I should start. Okay, because there's a lot of people coming in. So, no. It will continue. Okay. Okay. Then. If you wait until the last one, you will not say. Then I want to say a word. Okay. Then I start now. Beyond the fallen world lies the Arctic paradise. Sail far enough out to sea, and you come to the sun, the stars, and God. People relied upon myths because no one knew what the Arctic looked like. If the Earth was flat, the Arctic had to be on its absolute outer edge, halfway to outer space. The age of heroic adventures started in the late 1800s. It was then no longer the hope of finding God that motivated the voyagers to explore the northern unknown. Instead, scientific interest and nationalistic heroism, with its obsession to reach the North Pole first, motivated them. And here you see a picture of the center's foremost celebrity hero that was named Nordenskjöld, who embodied the ideal, tall, solitary, straight, and wrapped in fur.
The greatest impediment to exploring the Arctic was the ice floes that posed catastrophic dangers for the explorers' wooden ships, which could be smashed by the power of these enormous masses. Finally, on September 7, 1991, Oden, the pride of the Swedish icebreaker fleet, which shifts 2 meters of ice at a speed of 2 knots, was the first conventionally powered ship to reach the North Pole. This is a picture where I sit somewhere in that crowd, and I was happy to be on this ship. And here you see the picture on board ship telling us that we were at the North Pole. Despite the access to modern icebreakers, the Arctic Basin remains one corner of the world, both unexplored and difficult to explore. No place on Earth holds information so vital to an understanding of how climatic change would keep pace with environmental threats. One really good marker of that Arctic climate change is ongoing, in that we see a remarkable decrease in summer ice extent over the Central Arctic, with about 20% since 1960. The reduction of ice is most striking for the multi-year ice. And here in the picture you can see a difference of the multi-year ice that are 5 to 10 years old between March 1988 to March 2010. So the challenge lies in, is it possible to prevent summer multi-year ice melt? And one could prevent that if we can get an earlier freeze-up that in turn can lead to thicker ice and ultimately more multi-year ice in the following years. Clouds play a key role in regulating surface energy fluxes that affect how the sea ice freezes and melts. In particular, during the late summer, when the albedo of the sea ice is at its minimum, cloud albedo could control the timing of the autumn freeze-up. In over the pack ice, we have what we call optically thin clouds, which are clouds with fewer but larger droplets. So therefore, a small change in their droplet size and number is very important to heat transfer to the ice and thus to sea ice extent and thickness. The optical color of these optically thin clouds are in turn dependent on the number of particles available for uptake of water in sizes about larger than 100 nanometer in diameter, which we usually refer to as cloud condensation nuclei, or CCN. So if the effect of cloud optical properties on how the ice freezes and melts could be fully understood, the source of the summer high Arctic CCN needs to be specified. The longest record of monitoring aerosol numbers comes through the locations of baseline station at the fringes of the pack ice. From Alert, from Barrow, from Ny-Ålesund. And the picture shows a sulfate aerosol concentration in micrograms per cubic meter as a temporal development from January to December. And what is striking here is the strong seasonality of the aerosol temporal distribution in the Arctic, where we have the polluted period that we call Arctic haze. And in the upper right corner, you can also see the record of black carbon that comes from the Ny-Ålesund station on the Zeppelin on Spitsbergen. The opposite shows in the summer, when the air is very clean, with a much lower concentration of sulfate aerosol, as we see here. If we turn to the inner of the pack ice region, up to the North Pole, there has been no other effort than 4 Swedish subsequent programs studying processes relevant to the formation of low-level clouds north of 80 degrees in summer, with the first expedition starting in 1991, followed by one in 96, one in 2001, and the last one in 2008. And here is a picture of their cruise trackers. So the result I'm going to show you this morning will then be very Swedish focused, but not so Swedish focused, because all our expeditions have been very sounded internationally, with every time about 10 to 15 different nationalities participating. One very important thing here for the continuation of my talk is to show you this picture of the transport of air to the inner Arctic in summer. And as you can see, the contact with the land areas where we could have a man-made sources of aerosols are limited. So we have a very clean air in summer Arctic. So we try to understand then the CCN concentration as its dependence on the length of time the air spent over the pack ice. So now we have warm, moist air being advected in over the pack ice. And in the graph I show cloud condensation nuclear concentration as a function of the number of days the air has traveled in over the pack ice. So, as warm, moist air advects in over the pack ice, losses of CCN to surface will be at maximum in the first or second day due to the drizzle and fallout of fog drops. So the drizzle and fallout of fog drops works like a filter for any air coming in over the pack ice region. Thereafter, the fog lifts and low stratoform cloud forms, and CCN losses should continue by depositions at lower rate. But is there possibly a source in over the pack ice? And one can rephrase that question: can brighter clouds affect freezing of the ice? So is it possible to in any way change the cloud albedo of about 50% to about 75%? On the left panel, you see a probability source function contribution plot of the CCN concentration, but I show the lowest 25 percentile. And thereby I show you the area which is most sensitive to a change in number concentration of CCN. So if there is a source in over the pack ice that under climate change could change, then we need to find out which these particles are or what they consist of. So 2 ways there is to change cloud condensation of nuclei. One way is to emit primary particles from the ocean surface. The other way is to have aerosol nucleation or newly formed particles being formed, followed by growth, ranging from about 3 nanometers up to 100 nanometers, where we have the preferred size of the CCN. So here is a picture showing a compilation of all 4 expeditions. And we'll see, you see the source region is in the inner part of the pack ice, and it shows also that we have a number source, both of CCN sizes and also of nucleation mode sizes. It also shows, which is very important here, that these sources, as is shown in the size distribution, is only valid if we have started to broke up the ice. So we are about around 30% open water for the last 5 days until the air is reaching the position of the icebreaker. So the idea is that now when the ice is undergoing change, that we possibly then could increase the sources of the CCN in the inner parts of the pack ice. But which the sources are could be the next question. So what is seeding the clouds? The left panel shows an electron microscope picture of cloud water collected from a Zeppelin balloon at latitude 88 degrees north. If you then performed advanced liquid chromatography coupled with high selective sensitive tandem mass spectrometry, LCMS-MS, you can see that you have a number of sugars being present in the cloud water, pentoses, dextrosugars, and dexohexoses. And the hexohexoses are found in phytoplankton and bacterial secretions. And the pentoses and hexoses are associated with the cellular materials of phytoplankton. An independent study showed immunostated particles collected in the cloud water with an antibody specific towards the Melorrhizia arctica community from the surface microlayer. So both methods indicate that it seems to be a source from the surface water, the water in between the ice flows, from the uppermost layer that we call the surface microlayer. And that source of particles are defined from a biological point of view as marine gels. And they are defined as such because they can undergo volume transition, which I will show is important in this regard. The marine gels are three-dimensional polysaccharide networks interbridged with divalent ions to which proteins, peptides, amino acids readily bound. They are there because they are proposed to act as cryoprotectant and regulate osmosis in microalgae and bacteria. The size they come in various sizes, defined as particulate sizes that you have. We can start with the smaller sizes instead. By the way, the left panel shows a gel that consists of a collet size inner and attached to bacterium. And the lowest size of a marine gel it has a low molecular weight, dissolved organic matter that is less than 5 kilodalton. And there you more or less have the free polysaccharide chain available. Then you go into the most preferred size range that goes under the name colloids that are high molecular weight dissolved organic matter between 5 kilodalton and 0.22 micrometer. And then we have the largest particulate organic matter that is larger than 0.22 micrometer. And because the microgels, they have been identified for many years in the upper ocean surface, but they have only been identified as particulate polysaccharides because the techniques have not been able to detect any microgels smaller than 0.22 micrometer. And that goes, the larger than 2.2 micrometer goes under the labeling of TEP, if you maybe heard of that. So what we have succeeded with is to go beyond 0.22 micrometer in diameter and go then into the colloids and the dissolved forms of the marine gels. And on the left-hand panel, I show at the bottom a size distribution of these gels from the surface microlayer. And you see that you have around 7 nanometer peak and then like 50 nanometer peak and a few hundred nanometer peak. A very similar size distribution you see if you count the particles and size the particles in the collected cloud water. So it's time to ask the question, does CCN activation of gels occur at all? Then you need to go into chemistry of these gels, and you have to look upon their hydrophilic and hydrophobic properties, which make them not soluble in water. They don't go out as iron in water, but they can attract water molecules, so they are solvable in water. So water vapor do not uniformly condensate, since only part of the surface exhibits strong hydrophilicity and thus shows only partly wetting character below 100% relative humidity. And the right-hand picture now shows an electron microscope picture where you can see the little holes after water molecules, how they have been attached to this gel particle. This means also when you measure these particles out in field, they're going to show low hygroscopic growth factors because it takes time for the particle to be wetted, and that time is not given in the present measurement of growth factors. Once the whole surface is wetted, then the strong surfactant properties of these gels gives a decrease in surface tension, which leads to a decrease in critical supersaturation and promotes cloud droplet activation. So in the end, these are splendid CCN. And to sum up, we tested this in simulation by molecular dynamics. So you have this first step, adsorption of water on wettable surfaces, and the second step, strong surfactant properties promoting CCN activation. This behavior is not yet parameterized, so Köhler theory is not valid. The next question to be asked, is the gel theory on marine CCN origin consistent with primary marine aerosol observations? And here we see a first cartoon of particles, spray particles, being aided into the atmosphere by release of bubbles at a sea-air interface through jet drops and film drops, as bubbles are formed when air is entrained into the water induced by wind stress at the surface. Here we have jet drops in size of a jet drops as a function of wind speed. And there we have over the pack ice region a wind speed dependence for winds above 5 meters per second. If you look at a probability function distribution, both north of 80 degrees and north of 87 degrees, we can see that the winds are in general very low over the pack ice region. They are peaking around 4 to 5 meters per second. So the high wind speed are less frequent. So it's not so frequent to have this wind speed dependence, and it's even more evident when you go into the film drops, and there we have no whatsoever wind speed dependence of the flux of particles from the open leads. Okay, should we be worried about this? Yes, we were very worried about this, because if we have no bubbles and have no wind speed dependence of the bursting of these film and jet drops, how are they then getting airborne? But there are possible non-wind related sources of bubbles. So releases of bubbles trapped in melting sea ice, expelled by freezing water, or transported to surface by increased turbulence caused by supercooling conditions, respiration of phytoplankton, or precipitation. So we were very curious to see if we had bubbles in the absence of strong wind and only 10 to 30% open water. And here comes the final answer. Yes, we have bubbles in the water, then produced by a non-wind source. And if you see, this is the number population as a function of bubble size. And you see, if we compare what we measure in an open lead at 87 degrees north with open sea at lower latitudes, so you see for the bubbles, the smaller bubbles were all the way up to whatever, 30 micrometer, very similar to we have in open seas. So other mechanism than induced by wind stress at the surface. Which one we still do not know. So back to the gels now. The gel-colored particles will then be scavenged preferentially by rising bubbles in the water, and then end up be aided into the atmosphere by the burst of fin drops and jet drops. And here I show a picture of something happened to the axis there, but it's the concentration, it's the enrichment of gels or polysaccharides changed altogether here. But the bottom line is that the surface microlayer, colloid and particles, they are enriched compared to the below bulk water. So the gels are located preferentially in the surface microlayer, that is the top ocean layer. And this then the result of this will be that fin drops contain gel-colloid material with salt-free water from the surface microlayer with bacterium and debris attached. And the jet drops contain mostly sea salt, but also partly coated by particulate gels from surface seawater, the bulk water. And also of importance here is that we have not seen any sea salt large for particles smaller than 200 nanometer. And the implication of this is that the sea salt comes up at larger CCN sizes. And the larger a CCN is, if they are around 1 micrometer or even larger, they will become extremely few CCN. So they are not dominating at all the number population of the CCN. So you need to be in a size frame about 100 nanometer in order to make a significant contribution to the CCN number population or cloud rock population in the high Arctic clouds. Of course, one can worry about not finding any sea salt particles in sizes below 200 nanometers, as there are other that does that and present that in the reviewed literature. One example is Clark et al. From the Journal of Atmospheric Ocean Technology in 2003 that uses the volatility technique and conclude that particles from breaking waves were produced in all sizes between 10 nanometer up to 10 micrometer. And then I cite the paper that says size distributions were similar for heated and unheated distributions, confirming the particles' refractory nature consistent with them being sea salt. So with this indirect inferred chemical method, they conclude that sea salt particles can go way down below 200 nanometer. And that puzzled us also because we never saw that in our sampling or with different methods, and specifically not in the electron microscope pictures. So then we took the help with simulations again by molecular dynamics, and we created a cluster of gels on the left-hand side surrounding with sodium chloride. That is then to mimic the seawater. So at 530 degrees Celsius, and then we simulated a heating of this up to 530 centigrades, Most sodium and chlorine ions were concentrated on the surface of the polysaccharides aggregation to form a coating layer consisted of ionic crystal. So the salt ions put themselves as a cover of the gels. So it's therefore likely that the evaporated particles containing polysaccharides could exhibit a nature similar to that as sodium chloride. So these indirect volatility measurements could just be mistaken because of the nature of the gels and sea salt. Be aware of this when you compare this type of measurements in future. Another very popular way of studying the primary marine aerosol is through aided spray particles, that you have some kind of artificial bubble source, either on board ship in the lab or just on the surface of the ocean. And when you bubble artificially, you first of all mainly focus on the jet drops. And as I showed you a minute ago, the jet drops, they consist both of gel and sodium chlorine. So when you try to interpret these type of measurements to be what the real world does to us, then you have to be careful, because you are not able to sample the surface microlayer. You're ripping off the surface microlayer and get a combination of both the bulk water and the surface microlayer, and by that your measurements will be falsified, or you will be difficult to interpret your measurements from the atmospheric point of view. The size of a jet drop is also the size in particles where we have a down to that size that we have a technical development in using nanoscale chemical mapping by local infrared fingerprint spectroscopy, which is a very promising technique where you can actually really be certain of that you have the proteins, the amino sugars, or polysaccharides. And here I show a beautiful picture of the sea salt crystal in the middle and the gel particles surrounding this. But still, we are limited by size, but improvements will come, I'm pretty certain about this. And I'm presenting quite a few pictures with the electron microscope technique, because that is the only way to go around to study how a CCN source can change, because we need to study the number of individual particles. There are other techniques around for that, but electron microscopicity is a very good technique for studying individual particles. So I'm not at all referring here through my talk to any bulk chemical measurements, no mass. I'm only referring to numbers. Okay, next question to be asked. Is the gel theory of marine CCN coupled to the sulfur cycle? It could be many of you sitting in here that think, oh, where is CLOR? Shouldn't DMS be a player in this system? And so we thought in 1991 when we had our first expedition. And the result that came out in these panels, the CLOR, by the way, if you haven't come across that, is that you have a component DMS, dimethyl sulfide, being produced by phytoplankton when they die in the upper surface waters. And by turbulence and diffusion, the gas will reach the atmosphere, where it undergoes photochemical oxidation and be turned into methane sulfonic acid, or MSA, sulfuric acid, and sulfur dioxide, which can then undergo gas to particulate phase conversion or growth in the atmosphere and turn out to be particles in the end. So, at the right-hand panel then show a seasonal temporal development of DMS in the ocean, DMS in the atmosphere, and methane sulfonic acid as a particulate, and also non-cesial sulfate as a particulate. And they are very similar in their development, with about 30 degrees decline, a 30% decrease per week. So what did we learn about the DMS source? Yeah, we learned that the model ice zone and the waters nearest to the ice edge are the most biologically productive. And the right-hand panel in the lower picture show the concentration of the MS in the water at the open ocean and at the marginal ice zone. And I marked the word average. That is much lower than what you expected can find at a model ice zone in the high Arctic, with a peak in June, July. Then the red dots represent the concentrations measured in over the pack ice. And you see, firstly, that the season is shifted. So you have the peak in season in August, but you also have 100 to 200 less numbers available. So DMS concentrations are very low in over the pack ice region. Therefore, the model ice zone is responsible for feeding DMS in over the pack ice. And it does that through advection. And you see the main source of DMS in the very productive areas around Spitsbergen, south of Spitsbergen. And you have the advection in plumes in over the pack ice. This is from a modeling study. Through that advection, DMS then have an exponential decay of about 2 days. So the right-hand panel now shows the 0 is at the model ice zone, and the time is days or hours in over the pack ice, and you have concentrations on the y-axis. So you can see this exponential decline in DMS, both modeled and measured, and you can also see one of its oxidation products, sulfur dioxide, being increased after like 12 to 24 hours in over the pack ice, given off possibilities for new particle formation as hypothesized by Claude. So when we had this graph, the right-hand graph up, I became very satisfied because I lived in the area of Claude, and I could have CCN as a function of mass of sulfate. And you see the other remote marine areas in blue, the blue bar, and in the Arctic, inner Arctic, the air is so pristine, so you have the purple dots below, extremely low numbers, but it also shows how sensitive the CCN number concentration and then also the cloud droplet concentrations are to be in the inner part of the Arctic. So, correlation do not prove a causal relationship. Be very careful, young students here, be very careful. You can become happy for a few hours or even days, but you have to be careful. So when we had the possibility to look into these sulfate particles, they relieved a core of a gel sitting inside. So what we measured was the mass, which was correct, it was sulfate, but they were sitting on the number that was the gel. So it was not sulfate that was our source of particles, it was the gel. So now, when we know that the gels are there in larger size, we didn't have any sulfate on the particles unless the particle was larger than 50 nanometer. Below that, we only see gels. So then we have to ask us: what are the smallest particles? If they're not coming from the sulfur cycle, so what are they coming from? Because they are so small. So then I show you here a sequential number size distribution from about 6 hours of nucleation, and you see the nucleation mode at the bottom for these two. I also put in some sizes here, and a very common feature of the Central Arctic Ocean episodes of nucleation is a number enhancement of below 7 nanometer particles, accompanied by increased number in distinct size bands below 50 nanometer. So you get sort of a band behavior as each time you have a nucleation event. So it's hard to explain the hard Arctic finding. Hard to explain the high Arctic findings with the typical nucleation event followed by uninterrupted banana-shaped growth for several hours, a feature that is extremely common in all other areas of the world. So if this peak now is not related to the sulfur cycle, one have to rethink and go outside the box. So the increase in particles in the size range 10 to 50 nanometer diameters is therefore likely not caused by nucleation and growth. That is what we hypothesized. Disintegration of the primary emissions from the surface on the open waters between the leads may release to particles smaller than 7 nanometer that we call nanogranules that would then be mistaken for recently nucleated particles from homogeneous nucleation or heterogeneous nucleation processes. I show you the size distribution from the surface microlayer of the marine gels. So next question, is downsizing of atmospheric gel particles possible? That is, small particles from larger ones, because from the jet drops and fin drops came particles of the gels of around 100 to 1 micrometer in size, and now we need to go down all the way to a few nanometer. Is this possible in the atmosphere? Possible collapse of gels. Lowering pH causes sudden collapse of a non-porous arrays. These are from measurements of ocean gels. We know this. UV light splits marker gels into smaller units that cannot resemble either in water or in air. Bipolymer hydrolysis by bacterial enzymes. And additional DMS and DMSP cause collapse of polymer gels. So there are methods by which these gels can collapse. But can they collapse in the atmosphere? Is of course the most relevant question. We've seen this band feature of during the nucleation episodes being related to repeated haze and fog cloud cycling that seems to promote the marine polymer gels to collapse. So something seems to be happening inside the cloud droplets. And because of that, and because that we have seen the gels being extremely numerous in the cloud water, we have proposed a new road to explain nucleation that involves nucleation, condensation, and primary emitted nanometer-sized gel colloids from the surface microlayer. And here is an example from the case I showed, that if we only work with traditional homogeneous nucleation, that is the left panel, we have nucleation plus condensation, and we have the early growth by assuming 1.5 ppt of isoprene that was measured. And we compare with the right-hand panel that are the observation, and we see that they cannot mimic the observations, that assumption. If we assume the size distribution of the primary gel particles that we detect inside the cloud droplets, we show the B panel, we get, when we model, 2 bands, which is fine, but the reality shows that we need to have a growth also involved. So if we combine these 2 schemes, both a classical homogeneous nucleation with the availability of primary aerosols from the gels inside the droplets, then we have it's a result that intrigues, and we need to go back and try to understand this missing or the last link in what the gels can do for nucleation in over the pack ice. So next question, many questions here. So what are the connections between marine gel emissions and future environmental change, polar, coastal, and open ocean? So we have now seen that CCNs over the pack ice region could be changed if we change the source, that is the marine gel from the water in between the ice flows. So if we were to melt the ice even further, then a first assumption could be then that we remove a lid, and by that you get more particles up and start to change the cloud albedo from 50 to 75%. We also see that in each case, a gel component seems to have been an important internally mixed part of the particle for the CCN sizes. They are the right-hand, most right panels where you see the gels are inside, even inside and covered by the sulfur components. So not only having a physical removal of ice is of importance, you have to understand the biological processes of production of gels in over the pack ice in order to see if it is possible to change the optical color of the thin high Arctic clouds. So now we need to know something more about marine biology and talk about primary production both by ice algae and by phytoplankton. The ice algae, they are sitting in the porous channels in the ice, and the phytoplanktons are formed on the upper surface of the ocean. So the porous nature of sea ice not only opens a pathway for exchange of organic matter and with the seawater below, but also provides a habitat for ice algae. So the more the porous the ice melts, the more organic material can then enter into the surface water. But it's also governable for making gels and biology. So, and the porosity increases in melting ice because the algae will protect themselves. They go from around 70 per mil salinity out to about 32 when they drop into the water. So that is an enormous challenging for an ice algae to face. So then the gels can be produced to help them in this change. They also, the temperature will change, and the availability of water and light will change. So in that perspective, the gels will be governed by the ice melting. So biologically protective gels precondition the bottom ice layer for optimal habitability. And these Melrosea arctica algae that we found up in the clouds are very good gel producers. So not only that we remove the ice, but also that we melt the ice seems to govern gel production. Then what will govern phytoplankton production in the open water is, as a start, water column seeding of the ice algae and nutrients by melting ice will provide a starter community for phytoplankton growth in the water. So you actually also need the ice algae in order to start the growth of the phytoplankton community. And here you have an evidence of that when we measure the colloids and particulate gels, both in the surface microlayer and both in the ice algae, and you see the trace of fucols going from the ice algae all the way into the gels that have been produced by phytoplankton. So they are interlinked. But the phytoplankton, they live, when you talk about phytoplankton, you talk about phytoplankton primary productivity that should be high. And one component in that is light. And light is going to be governed by if we melt the ice. More light will reach down to the water. So that is a positive sign. But at the same time, as we remove the ice, we will have less of the very low saline water on top of the high saline Atlantic water. So we will extend the mixed layer, which has an implication for light penetrating down and actually making the bloom to happen. And here you can see that light very, very easily levels out. Already 10% is only left at around 5 meters depth. And you can see that the primary production that I have shown in the insert in red and yellow and light blue is only confined to the uppermost few meters of the Arctic basin. So there is where you have the production. And you also have nutrients coming out when the ice melts. And for the phytoplankton primary productivity, you have then various factors impacting that, but the most important are if we have nutrient availability, and if the ice goes away, you will also have less of the nutrients. So you hear here now I say this and that and that and this. So there are many options now from a biological point. If you think the atmosphere is complicated, the biology is far more complicated. So this is just a little cartoon showing, I'm not going to do any detailed study of that. You can see the left panel shows how it is today, that you have a seasonal ice zone with high productivity and a model ice zone, and a multi-year ice zone in over the pack ice with low productivity. In the future, one thinks when the ice goes on the further melting, that you will get the whole pack ice as a very productive modular ice zone. That is the estimates. So, how many more minutes do I have? No, but I need to finish up here. So the question now I will finish with. So, is there a biological control on the formation of cloud droplets over the Arctic pack ice area? Yes. Does DMS control the optical properties of the high Arctic clouds? No. They are the gels. Will biological activity and production of CCN increase or decrease with melting of the ice? To be continued, because it's very complicated. Then I need to. I apparently have to skip a section here, but I will still end with a few slides. Let's see. If you want to have further reading, ACP, ASCO special issue, and I want to go back to the age of heroic adventures. And one of them is named Fridtjof Nansen, that lived between 1861 and 1930, who managed to combine in one person not only a scientist and a heroic adventure, but also a risk-taker of the highest order in his obsession to reach the North Pole first. Nansen became Norway's national hero and received the Nobel Peace Prize in 1922. But what would have happened if Nansen, not one afternoon in 1896, after 18 months afoot over the ice, had encountered in Franz Josef's land another Arctic explorer, Frederick Jackson, who had access to a ship? You see, Nansen wasn't just heroic, he was lucky too. And weren't we very lucky to, in 1991, have a very modern icebreaker that could reach the North Pole for the first time? So one realizes in the end how mercifully the sun shines in the summer Arctic, this most desolate of hinterlands. It is here that the sun has chosen to stand watch day and night to preserve the rest of our world and life itself. And I want finally to thank all the members of the High Arctic Expedition, thank all of you for listening, and of course thank all the organizers for giving me this opportunity to show you what we have done for the last 25 years. Thank you.
Thank you very much. We would like to open the discussion by reminding you to please wait for a microphone before you pose your question. Then you can also probably produce this nice kind of echo. Please also remember to mention your name and affiliation when posing the question. And I would like to emphasize that we encourage the younger people here to ask their questions as well. You note I leave you with something relative here, so it's up to you to decide if you're younger. Please.
No question.
To break the ice, let's give the first question to an old man. Yeah, so it's actually rather a remark than a question. I think it's great that you find another way for forming small new particles, because the cloud experiment has actually shown that sulfuric acid cannot do the job, at least not alone. You need other ingredients, and if there is none, you will not form sulfuric acid 10 nanometer particles just from this sulfuric acid. So I think I would like to congratulate you on this way out, so that we have a new hypothesis to work on.
Thank you. It looks very promising. We just have to show how these particles are entering out of the cloud droplets, but it looks very promising. One question.
Yeah, no, James, wait, I think it's...
So we can already say name and affiliation, James Allen, Manchester. And I'd say he qualifies for a younger person.
Yeah, just question regarding your comment about the lack of a link with the sulfur cycle. I mean, you were showing the electron micrographs are showing the biological material embedded in the sulfur. Could it not be hypothesized that, given the fact that the biogels aren't particularly soluble, that they still require coating of sulfate in order to be considered viable CCN?
I think you bring up an important issue here. The gels themselves can do a good job in being, it seems like from modeling as a CCN, but to have sulfate or any sulfur components surrounding them is also a very good business. So I focused a lot on gels now, but I think maybe I should rephrase a little bit that I think it's a marriage between the gels and the sulfur cycle that eventually will give very good CCN. But the number population is governed by the source of the gels.
So in the absence of any other questions, we allow for Caroline to show us some extra slides. The time allotted for this is 5 minutes.
Yeah, it will be shorter. Yeah, sorry, here I am again. I think I spoke a lot of this biogenic source of particles. But of course, there is a worry that we bring in pollutants in over the pack ice. And they come from a likely source of them is from the forest fires that surrounds the Arctic pack ice region. And we have studied this also because we have measured the vertical distribution of particle. And we can see that about an average 12% of the fires in the summers of 2001 and 2008, as an example, reached the inner Arctic. So even if we have a fire, it doesn't seem to be very frequently reached in over the pack ice. The air that comes in over the pack ice from the fires, they are lifted at the Arctic front along the potential temperature surfaces, which means that when they reach in over the pack ice, they come at very high altitudes. And this is the right-hand plot is an OPC, particles larger than 300 nanometer in a biomass burning plume, because we also had measurements of acetonitrile at the same time. And you see that they are very aloft in the atmosphere. Here you can see where I marked the Arctic boundary layer in orange, where I talked about the clouds being to sit. So it's a very large distance between the boundary layer and the aloft layers where the plumes come in. And here is an enlargement of the Arctic boundary layer that overall is a stable Arctic boundary layer. So the high Arctic boundary layer is typically a shallow, well-mixed layer at the surface, typically only a couple of 100 meters deep, capped by a temperature inversion below a stable stratification of the air in the free troposphere. These characteristics limit the mixing of particles from elevated plumes in the free troposphere into the boundary layer. The only mechanism that can bring elevated plumes down to the inversion is by large-scale subsidence, which is a very slow process, which happens, but it's a very slow process. So thus long-range transported biomass burning or pollution plumes are not considered to have any direct significant contribution to the aerosol population in layers close to the surface. So if they're going to have any significance, for example, black carbon, we need to make black carbon soluble in water. So we need to get it some hydrophilic properties. When we measure black carbon at the surface, the levels only come up to a few nanogram per cubic meter. So first we need to change the chemistry of the black carbon, which could happen. We've seen that at other places. But we also need to have the plume coming in at the top of the clouds in the boundary layer. And then thirdly, we need to have the clouds to precipitate. And all that in place is less than a few % of all plumes from the Siberian fires that reaches in over the pack ice and becomes significant for the snow. Thank you.
Okay, thanks again, Caroline. Let's thank her again. This concludes our first plenary, and I would like you to wait here because we have some housekeeping announcements.